New section, the Euclidean Algorithm. Recall that we have already seen the notion of the greatest common divisor of two integers. Among many things, we first of all saw that if we are given two integers, not both of which are equal to 0, then their greatest common divisor exists and is of this form, where x and y are some integers. That is, if a and b are given to us, then some integers x and y can be found for which the GCD of a and b will be a linear combination of a and b with those integers as coefficients. Now, in this section, we ask the question, okay, if we know what the GCD of two integers is, we know the definition, but if we literally follow the definition, then the task becomes more and more unmanageable when the numbers involved become larger and larger. That's how we start this section. See, the author says the greatest common divisor of two integers can of course be found by listing all their positive divisors and choosing the largest one common to them, which is just what the definition says, or which in fact even the name itself says that same thing, greatest common divisor. That means you find all the positive divisors which are divisors of both the given numbers, and you find the greatest one among them. For example, if you say take these two integers 12 and 18, let us list all the positive divisors of 12 first. 1 definitely divides 12, and this gives rise to another divisor which is 12 itself. 2 divides 12, which gives rise to 6, which also divides 12. 3 divides 12, which gives rise to 4. And that's just it, because 5 does not divide 12, after which the things will repeat. You get 6 and then 12. Just like that, if we list all the positive divisors of 18, we get 1, 18, then 2, 9, 3, 6, and that's just it, because 7, 8, after 7 and 8 we will go to 9 again, and that's it. After 9 the next multiple is 18. Then what we do, among these positive divisors, we locate the common ones, 1, 2, 3, 6. Anything else? 9 does not appear here, 18 does not appear here, and that's just it. So these are the common divisors. One, 2, 3, 6. Among them, the largest one is 6. So, by the very definition of GCD, this is equal to 6. However, you can imagine what will happen if these numbers are very large. Finding their forget about common divisors, finding their divisors itself becomes an extremely time consuming task. So that is why, but this is cumbersome for large numbers. A more efficient process involving repeated application of the division algorithm is given in the 7th book of the Elements. Euclid wrote the book's Elements. No. So in the 7th book of the Elements, an algorithm has been found which bypasses this cumbersome process of actually literally applying the definition and finding the GCD by repeatedly applying the ordinary division algorithm, by which we know that when we are given two integers, at least one of which is non-zero, then you can divide by the non-zero integer that other integer to get a quotient and a remainder, so that the remainder is non-negative and is strictly less than the absolute value of the divisor. So that thing we can again and again apply repeatedly to ultimately get the GCD, and this process is known as the Euclidean algorithm. Although there is historical evidence that this method predates Euclid, in fact it was there before Euclid, but Euclid of course assimilated all the materials, and he had this thing in his 7th book, and that is why today it's referred to as the Euclidean algorithm. So let us now see what this thing is about. This is something you probably already know, and in fact we have seen it already in our algebra videos, but because this is another text, so let's just go through it once more. It goes like this: the Euclidean algorithm it's a name now, so capital A. May be described as follows. So we will be given two integers. It is not mentioned here, however, that at least one of them has to be 0, but we already know that condition. So when we are talking about GCD, that assumption is there in the background, okay, although it may not have been explicitly mentioned. Let A and B be two integers whose greatest common divisor is desired. So we immediately okay, yeah, but whatever I just said now about this Euclidean algorithm, that when we are given two integers A and B, at least one of them has to be non-zero, so you can divide the other integer by the non-zero integer to get a quotient and a remainder, and then the process will be continued in some way. But because signs of integers they don't play any role in calculating the GCD of two integers. What I mean by that is this: if A and B are two, say, positive integers, then we have already seen, in fact we mentioned this before, that GCD of A and B is equal to the GCD of minus A and B, that is equal to the GCD of A and minus B, and that is equal to the GCD of minus A and minus B. And this thing happens because the GCD by definition is a positive integer. So, and it is what? According to definition, it's the largest among the positive common divisors. So positive common divisors of A and B are the same as the positive common divisors of minus A and minus B, for example. or the positive common divisors of minus a and b. So that's what we mean when we say that signs don't affect GCD. So that is why, although these two integers may be positive or negative or any possible combination, but it's enough to consider only the positive versions of them, that is considered their absolute values. So that's why in the next line the author says this, so that we don't have to deal with negative integers unnecessarily, because the GCD of the absolute value of A and the absolute value of B is equal to the GCD of A and B there is no harm in assuming that A is greater than or equal to B and B is greater than 0. That is, what we are assuming here is that both A and B are positive, and of course one of them will be greater than or equal to the other. Without losing generality, we have assumed A to be greater than or equal to B. Okay, now how do we apply division algorithm repeatedly, and what are we going to divide and by what? So the procedure starts like this. The first step is to apply the division algorithm to A and B. Is to apply the division algorithm to A and B to obtain A equal to, this will again and again appear, quotient remainder, because we are going to again apply the algorithm, so it's better to number them. So here what we have done, we have divided A by B. We can do that because B is positive, or more specifically, we don't really need positivity for division. B is non-zero. So this is quotient, this is an integer q1, this is an integer r1, where r1 satisfies this inequality. So we have just simply applied the division algorithm to A and B. Now this r1 may or may not be equal to 0. If r1 is equal to 0, that is one case, then if r1 is 0, then B divides A. And we have GCD of A and B equal to B. Now if r1 is not 0, then next we divide the previous divisor B by the remainder r1. Okay, so that will be another application of the division algorithm if r1 is non-zero. When r1 is not equal to 0, we have, or what is the exact language the author is writing? Divide b by r1 to produce integers q2 and r2 satisfying b equal to q2 r1 plus r2, where the current remainder r2 is non-negative and is strictly less than r1. Now you can understand how this proceeds. Again, if r2 is 0, then r1 divides b. Okay, r1 divides b, so the GCD of b and r1 is equal to r1. However, but then that is the GCD of b and r1. So what is its relationship with this GCD? We are coming to that. Okay. If r2 is 0, we stop and we have this thing. But what do we do with this information? We will come to that. Here itself, the author does not write anything about this case. We will see that. Otherwise, you continue this process. You see, the process is this. First we have divided a by b and we have got quotient and remainder. Then divide the divisor by the remainder. Here. Again we get another quotient and remainder. If the remainder is non-zero, again divide the divisor r1 by the remainder r2. To obtain integers q3 and r3, satisfying, so we are dividing r1 by r2, q3 r2 plus r3, where the current remainder r3 is non-negative and is less than r2, and the process goes on like this. This division process continues. until we get a zero remainder. Until some zero remainder appears. And the question is, what will happen if a zero remainder does not appear? That will never happen. Say at the n+1 stage. The reason for eventually getting, let me just first complete the sentence. At the n+1 stage, where Rn-1 is divided by Rn. So what we are saying is that, let's just again go through to familiarize ourselves with this process, with this algorithm. Let's once more go through this. A has been first of all divided by B, that gives us quotient Q1, remainder R1. The quotient is not that important, not yet. Okay. Now R1 may or may not be 0. If R1 is 0, then immediately we have got GCD. If R1 is non-zero, then R1 is positive. In that case, divide the divisor B by the remainder R1, which now is a positive integer. So that will give you quotient Q2 and new remainder R2. If new remainder R2 is 0, then we stop. Here we don't say anything about what will then happen. That is where coming to that. But if the remainder R2 is also positive, then divide the that divisor, the previous remainder, by this new remainder to get quotient Q3 and remainder R3, which again will satisfy these things. Now the question is, if this process keeps on going, will it ever end? It will end, but before that, let us just see. This division process continues until some zero remainder appears. So our doubt is that what happens if a zero remainder never appears? Now that cannot happen because of this. A zero remainder must eventually appear. A zero remainder occurs sooner or later because the decreasing, you see, every time we are having a non-zero remainder, say R1 is non-zero, then the next remainder is R2, which is non-negative and strictly less than R1. The next remainder R3 is non-negative and strictly less than R2. So all the non-negative integers are, we are only getting non-negative remainders, because remainders are by definition non-negative. But every step is giving us a still smaller non-negative remainder. So this process obviously cannot go on indefinitely, because below B, that is less than B, there are only finitely many non-negative integers. So sooner or later we are bound to get a zero remainder. There is no other choice. Remainder sooner or later because the decreasing sequence B greater than R1, which is greater than R2, greater than or equal to 0 cannot have more than b integers. So a zero remainder appears, and we have now assumed that, say, at the n plus 1 stage a zero remainder appears. At the n plus 1 stage we have the remainder Rn minus 1, which is being divided by the next remainder Rn, and this division is complete in the sense that Rn minus 1 is divisible by Rn. So that's where we get a zero remainder. In other words, according to these notations, Rn plus 1 is 0. So far we have been just going on dividing some divisors by remainders, and again dividing those remainders by other remainders, but we still don't know why we are doing these things. Anyway, if you continue this procedure and you have got the equations, then these following equations appear. The result is the following system of equations. The first one is, of course, dividing a by b to get quotient q1 and remainder r1. This is accompanied by the inequalities that r1 satisfies. Then next we divide b by r1 to get quotient q2 and remainder r2. And because the procedure continues, so this possibility is not there. R1 is actually greater than 0, and that's why we have this next step. Just like that, R2 say is greater than 0 and is less than R1. Then let's write another one. Next we divide R1 by R2 to get quotient Q3 and remainder R3, where R3 satisfies these inequalities, and it goes like this. Eventually we reach, at one stage we reach Rn minus 2. So that is now being divided by Rn minus 1. And here maintaining the pattern of these things, these suffixes, what we have to write here, this plus 2, no. So this is Qn plus Rn, where Rn satisfies these inequalities, and in that next step Rn minus 1 is equal to Qn plus 1 Rn plus 0. Okay, so this is where we get the first zero remainder. First zero remainder means only zero remainder, and there the process stops. Let me just also see one more thing. At the n plus 1th stage, n plus 1th stage they are saying, na? How many stages are there starting from R1 to Rn minus 1? N minus 1 stages. plus these two stages in the beginning. So that's how we get n plus 1 stages. At the n plus 1th step or stage, we are getting the zero remainder. Okay, fine. But what is the purpose of all these calculations? Our claim now is that this last non-zero remainder Rn is actually the GCD of A and B. Okay, that's the thing. We argue that Rn, the last non-zero remainder, that appears in this manner is the greatest common divisor of A and B. Is GCD of A and B. Now we will prove this, and in this proof we first need a lemma. The proof is based on this lemma. There's no number, just lemma. If A is equal to QB plus R, then the GCD of A and B is equal to the GCD of B and R. We need to prove this lemma first. Since this lemma comes after a discussion like this, so you can understand that although we are not saying anything about these quantities A and B particularly, but you imagine that A and B are actually positive integers, because that's how we went through the discussion here. And in fact, this is where we need to apply the lemma. So it's enough for us to consider A and B to be positive integers. And because of that, since A and B here, of course, both are positive, so GCD exists. But here B is positive, so even if R is 0, this second GCD also exists. Okay, so this equation makes sense. I mean, one can ask whether this equation is true or not. Now we are going to show that this is true. So we start off by giving a name to this GCD. Let D be the greatest common divisor of A and B. Now because D is the GCD, so by definition D divides both A and B. Since D divides A and D divides B, we have D dividing A minus QB. using the elementary properties of divisibility relation. So D divides A minus QB, or the same thing, D divides R. So what do we see from this? D is a common divisor of B and R. Thus, D is a, and not just a common divisor, a positive common divisor. Why positive? Because D is already the GCD of something. So by definition, D is positive. So D is a positive common divisor of B and R. Our aim is to show that D is equal to the GCD of B and R. So for that to be true, next we will show that any common divisor of B and R is less than or equal to D. Let C be a common divisor of B and R. We need this equation. Well, we will again write them if when we want. B and R, i.e. C divides B and C divides R. Then C divides QB plus R, or C divides A. Because A is QB plus R. Hence, C is a common divisor of A, and already C was assumed to be a divisor of B, but now we have shown that it divides A also. So it's a common divisor of A and B. Thus, but D is the GCD of A and B, the greatest common divisor. So by the definition of D, C is less than or equal to D. So see what we have achieved. We have proved first of all that D is a common divisor of B and R. Next, taking a common divisor C of B and R, we have shown that C is less than or equal to D. So by the definition of GCD, D is also the GCD of B and R. And that's what we wanted to show, because D is this thing. So this completes the proof of the lemma. Okay, now we are going to use this lemma to have our, whatever we were claiming back then, that Rn is the last non-zero remainder is the GCD of A and B. Now we can justify that claim. But before that, let me just, I think I'm already running out of ink and we need those equations. I will write that on this side. So the equations were this. First of all, how long will it take to come? A has been divided by B to produce the remainder R1. Then B has been divided by we won't need those inequalities now. B is next divided by R1 to produce the remainder R2. Then R1 has been divided by R2 to produce the remainder R3, and it went on like this. At the nth stage we have got this Qn Rn minus 1 plus Rn, and at the n plus 1 stage we have got complete divisibility. Okay. Using the result of this lemma, we simply work down the displayed system of equations. To get, so let us also write, because we are going to use this fact, that if A is QB plus R, then GCD of A and B is equal to the GCD of B and R. So GCD of A and B is what we start with. That is equal to, according to this first equation, that is equal to GCD of B and R1. So we have used this. Then by the second equation, GCD of B and R1 is equal to GCD of R1 and R2. Then by the third equation, this GCD of R1 and R2 is equal to GCD of R2 and R3. So you can see that in this way, if one keeps on going, we will eventually reach a stage like this. I won't be able to completely write here. So this is equal to, at some stage, GCD of Rn minus 2, Rn minus 1, and by this equation, this GCD is equal to the GCD of Rn minus 1 and Rn. And in fact, by this equation, this can also be used. You see, in this lemma, we are not assuming R to be non-zero. R can be 0 also. That does not affect the lemma or its proof. So this is equal to GCD of Rn minus 1 and Rn is equal to GCD of Rn and 0. Now Rn is known to be non-zero, so this GCD exists and is equal to Rn. So that's how GCD of A and B is equal to Rn. If you continue this process of applying the division algorithm again and again, the last non-zero remainder that you have is the GCD. Which now we have demonstrated. So this is one thing. Okay, so we now have got an algorithm, and why are we saying this is an algorithm? Because it is a procedure so mechanical, you can write a computer program for this, and the computer will be able to calculate the GCD. Give the computer A and B, at least one of which is non-zero, it will calculate the GCD in some time. Now here another aspect comes out. You see, in theorem 2.3, theorem 2.3 is the result which proves that the GCD of A and B exists if at least one of them is non-zero, and it also additionally proves that the GCD is the linear combination of A and B. However, the proof or the statement of the theorem gives us no clue about how to find those integers x and y, using which you can write the GCD of A and B as, say, ax plus by, as a linear combination of A and B. But these equations will help us find those integers x and y. So using Euclidean algorithm, you can get actually two things done. You can calculate the GCD, and then you can again use those equations to express the GCD as the linear combination of the integers of which you are finding the GCD. This asserts that the GCD of A and B can be expressed as a, or in the form ax plus by. But the proof of the theorem gives no hint as to how one can determine the integers x and y. If you recall the proof, in the proof what we did, we considered a set like this, where x and y are integers, and then the GCD turned out to be the smallest positive element in this set. So the proof actually, we showed that such a smallest positive element exists, and that fact in turn comes from the well ordering principle, that the set of positive integers is well ordered, but that is an existence proof. The well ordering principle tells us that there is a smallest positive element in this set because there are positive elements in this set. But it does not tell us for what values of x and y that positive element is achieved. And that's where it fails. I mean, the proof is not a constructive proof, it's an existence proof. Now, however, we will be able to rectify the situation. Rectify means we can improve the situation and find the x and y. For this, we fall back on the Euclidean algorithm. This time, however, instead of starting from the first division step and going like this, we will start from here and go up. Let us see what we mean by that. Starting with the next to last equation. Next to last equation means this one. This is the last equation, the one before that. Arising from the algorithm, we write arising from the algorithm, we write. So we will write it in a slightly different manner. We will write Rn in terms of the other things. Let me write it here below. It will be more prominent. Rn is Rn minus 2 minus Qn Rn minus 1. Now solve the preceding equation of the algorithm. Algorithm for what? Rn minus 1, I think. For Rn minus 1 and substitute that to obtain this following thing. Okay, so what are we saying here after having this, which clearly is coming from this one? Then now solve the preceding equation, even the equation before that. Let's just see, let's write the equation before that. It will be Rn minus 3 equal to qn minus 1, we are adding 2 to this suffix to get this suffix, and this one, the next one, is 1 less than that. That means rn minus 2 plus rn minus 1. So from here we are saying that we have to solve for rn minus 1. That means rn minus 1 is equal to rn minus 3 minus qn minus 1 times rn minus 2. That we have to substitute here. Okay, so doing that we obtain this. Rn equal to rn minus 2 stays like that, minus qn times, now in place of rn minus 1 we are going to write rn minus 3 minus qn minus 1 times rn minus 2, and after rearranging things you can see that this becomes 1 plus qn minus 1 rn minus 2, this one and this one, plus minus qn times rn minus 3. Do you see one thing? In the beginning we had Rn expressed as a linear combination of Rn minus 1 and Rn minus 2. Then after some manipulations we have been able to express that same Rn, the last non-zero remainder, as a linear combination now of Rn minus 2 and Rn minus 3. So previously it was Rn minus 1 and the one before that Rn minus 2. Now we are going up, then Rn minus 2 and Rn minus 3. In the next step we will have a linear combination of Rn minus 3 and Rn minus 4 expressing Rn. This way if we continue, at one stage we will get to A and B. That's what the author next writes. In this general form of these equations, it may be somewhat difficult to see what is really going on. I mean, mechanically we are seeing that we are going through some calculations, but only all these things will be clear only when we see an example which is coming. Anyway, completing this thing, this represents Rn as a linear combination of Rn minus 2 and Rn minus 3. And continuing in this manner backward, through the equations or through the system of equations, same thing, we successively eliminate the remainders. It's about eliminating remainders. After this step, in this step itself, we have gotten rid of Rn minus 1. So one by one, the remainders are going. But in each stage, we are keeping that fact I mean, we are maintaining that fact that Rn is a linear combination of some things, and those things ultimately will lead to, in the final stage, a linear combination of A and B of the remainders Rn minus 1, Rn minus 2, etc., R2, R1, all these remainders. Until a stage is reached where A comma B is expressed as a linear combination of A and B. Now, to illustrate all these things, we consider one example. Actual numerical example. Which is this. Let us see how the Euclidean algorithm works in a concrete case. By calculating say this GCD. By calculating the GCD, no say. GCD of 12,378 and 3,054. So we start off by dividing the larger one by the smaller one. Here there is something to be said. Let us first go through the process of applying the division algorithm again and again. Let's find the last positive remainder, which will be the GCD, and then I will say something about this, which one should be divided by which one. The appropriate applications of the division algorithm produces these equations. So here we are of course dividing the larger one by the smaller one. You can of course verify these calculations using a calculator, or if you really want you can do it on paper also. $3054 turns out to be equal to 18 times 162 plus 138. Then 162 is 1 times 138 plus 24. These are not decimal points, okay? These represent multiplication. When you see the dot below at this level, that is decimal point. When you see it in the middle as a central dot, C dot, it denotes multiplication. Between numbers. In other cases, for example, between vectors, it denotes a dot product. So it's not decimal point, that's the thing here. And then 138 is 5 times 24 plus 18. Two more are there, which I think I can cram here. And 18 of course is divisible by 6. 3 times 6 plus 0. So at each stage you can understand that these numbers that are appearing on the right hand side, the rightmost numbers are the remainders. There is no need to write those inequalities. It's obvious that these are all positive up to 6, and at each stage the remainder is less than the divisor. 162 is less than this, 138 is less than 162, 24 is less than 138, 18 is less than 24, 6 is less than 18. And here of course the remainder is 0. So the last non-zero remainder is 6, and that's why the GCD of these two numbers is 6. You can understand how efficient and how easy this process is. You don't even have to think about the factors of these numbers. If you really want to apply literally the definition of GCD to these two numbers, first of all, what will you need to do? You will need to factorize these numbers, find all the divisors, and then see which are the common divisors and which the greatest one among them is. However, here no need to do those things. You can divide like this, and this procedure is mechanical. Okay, finding quotient and remainder. So it is much faster than the literal definition. Now the next job, this is not over yet. We have found the GCD, but we will now use these equations to express the GCD6 as a linear combination of these two numbers. But before that, let me tell you something about this starting point. Say you decide to divide this by this and not like this. You don't decide to start like this. What will happen? Will the process not give us the GCD, or will it give us a different GCD? If that happens, then there is a problem with this process. Luckily, it does not affect your final answer. It does not matter where you start, which one you decide to divide by which one. Had we decided to divide this by this, what would have happened? because this is greater than this, so the quotient is bound to be 0. And the remainder is this number itself. From the division algorithm we know, because once we find an expression like this, an equation like this, the division algorithm tells us that the quotient and remainder are unique. From there we know that this has to be the quotient and this has to be the remainder. But there is another way of looking at it without going to the without appealing the division algorithm itself. You see, because this number by which you are dividing is greater than this, so if here you don't have 0, if you don't have 0 here, if you have something positive, then this will either stay the same or it will increase. In order to get this number from that much larger number, you have to subtract, not add. Or in other words, you have to add a negative number, and remainders by definition are not negative. If on the other hand you have a negative number here, then this is very large and negative. So in order to get this thing, you then have to add something which is much larger. Okay. In this case, however, I think we are not able to justify that readily, but you can understand what I am trying to say. You have to have the remainder 0 here. The quotient 0 here. So what do we get? So this is our new first step, and from this new first step, this remainder is of course non-zero. So the process continues. In the next step, what we will do, we divide the divisor by the remainder, which is nothing but this step. So if you decide to start like this, then in the very next step you have this thing, from where also you can start in the other case. So it does not matter which one you choose to do first. That's the point here. Okay, so before we go to the thing of linear combination, our previous discussion, we need to conclude. Discussion makes us conclude or tells us that which is in our case 6 is the greatest common divisor, that is this. Okay, now next we come to that, expressing 6 as a linear combination. And 3054, we start with no need to again write those things. We proceed as below, because we are anyway going to do the actual calculation now. So we start with the next to last equation. This is the last equation which we do not touch. We start from here. So first we write 6 as 24 minus 18. There's no point writing 1 times 18, so we simply write 18. Okay. In the very next step, what you do, which I think it's better to write there. We have used this equation, so we have expressed 6 as a linear combination of whatever we had in this equation. So this equation is gone. Next, you use the equation above that and express 18 in terms of the remaining things. So 24 minus 138 minus 5 times 24. In the next step, you rearrange things. Minus 1 times minus 5 is 6. 6 plus 1, 7. So 7 times 24 minus 138. So then you substitute for the next higher one, 24. So this is 162 minus 138. Minus outside we have 138. So this becomes 7 times 162. Minus 7 minus 1 is minus 8 times 138. Okay. Next we substitute for 138. 7 times 162 minus 8 times 3054 minus 18 times 162, and this calculation is big. 7 plus 8 times 18, which of course we can do by hand, but why? Since I have the things written here for me, so it will become 132 times 162 minus 8 times 3054. Okay, so 7 plus 8 times 18 is 132. And finally, we express this last remainder, 162, which is according to our notation R1. Q1 is 4, R1 is 162. 132 times 12378 minus 4 times 3054 minus 8 times 3054, and these we don't need anymore. So this ultimately turns out to be, let me also see whatever I have written is correct. 7 times. hold on, have I made a mistake here somewhere? I think I have made a mistake. 24 minus 18, 24 minus 138. Oh yes, what the hell, this is 6. No, I have written 7. This is 6, so this is 6, and that means this is 7. Yeah, now it is becoming 130. Yes, I would have caught this mistake had I calculated this. Anyway, so this is now 7. So now ultimately it becomes 132 times 12,378 plus minus 535 times 3054. So our x is 132 and y is minus 535. We thus have x equal to GCD of 12,378 and 3054, that is equal to x plus y, where x is 132 and y is minus 535. So we have found one way of expressing 6 as a linear combination of these two integers, but this is not the only way. Note that this is not the only way of expressing 6 as a linear combination of our numbers. Among the other possible ways, among other possibilities, just to show that this expression, this linear combination is not unique, we can do this. We can add and subtract times 3054 to obtain this. So what we can do, we can add and subtract this number here. Because this number has both the given numbers, so things can be conveniently taken common out, and doing that you get exactly what that. Okay, so with this 3054 times 12,378 plus minus 535 minus 12,378 times 3054, so that minus this plus this, they cancel out. So here you get another linear combination, which is 3168 and minus 12,913 times 3054. So this example illustrates the Euclidean algorithm. Using that, we have found the GCD 6, and using that those equations in the process to also express 6 as a linear combination of the given numbers. And then we have seen that that expression is not necessarily unique. So we are stopping the video here itself. In the next number theory video, we will see some remarks by the author on the number of possible steps that you may have to calculate in order to get the last non-zero remainder. That is also a question. No, if you can understand one thing roughly. If your numbers are very large, then most likely you will need many steps to calculate the GCD. But it may happen that one of your numbers divides the other. Then in the first step itself you will find the GCD. I mean, when you go for dividing the larger number by the smaller number, if immediately you get the zero remainder, then this itself is the GCD. The smaller number itself is the GCD. But I am saying that most likely you will take more steps for calculating the GCD, because in most situations that will not be the case. Non-divisibility is more than divisibility. But there are some remarks and some actual work has been done on that. Likely how many steps you will need to calculate in order to find the GCD. So those things we will see, and there are some other related things also. So we will see these things in the next number theory video. And tomorrow there is in the last week we went through Lee's algebra exercises. So tomorrow we have Gaussian algebra exercises. Next week again Lee will come. So tomorrow we will have two videos, one on groups and one on rings. Both will have Gaussian algebra exercises. So that's it for tonight. So see you tomorrow with Gaussian exercises. Until then, this is me, Lucifer, signing off from a mathematical room. Have a nice night.